Currently we have integrated the Xbox 360 controller with our prototype robot by mapping the joysticks to their respective gear assemblies. As the joysticks are moved, the robot responds by varying the analog speed of each motor. Here you can see the alpha version of our software. When the user moves the joysticks, the arrows indicate the current robot state and the video is refreshed in real time.
Our project resulted in successfully creating a robot that could operate a fire extinguisher and be controlled remotely via Wi-Fi communication. The robot has ample steering control and maneuverability, torque, and weight to navigate through non-ideal terrain and carry a payload large enough to allow for firefighting ability. The metal shielding makes the robot resistant to conductive and radiant heat and helps protect the components inside. This implementation is, however, not incredibly heat-proof. The rubber wheels and plexiglass camera window are prone to melting, and the components inside will also melt once the metal shielding is heated enough. The robot has experienced a battery life of around 3 to 6 hours of activity, as seen by this chart. A maximum of about 13 to 14 hours can be achieved in an immobile state. These values were obtained by measuring the amperage drawn from the battery at each speed and using the watt-hours of the battery to determine the life of one charge. One element of the original design that we did not implement was the maps integration with the GPS shield. We encountered difficulty in providing the robot's location on a satellite map. We implemented several methods to test the mechanical design of the robot and the correctness and performance of the software. We tested the mechanical workings of the robot by manually controlling it and observing the resulting behavior. Our initial interest was getting the robot to drive in the correct direction. For testing purposes, we created a Java program that converted keyboard inputs to commands that were sent to the robot. This allowed for mechanical testing without having to use the Xbox controller. We were able to verify that the motors were turning in the right directions with changing user input combinations, and that the speed was being adjusted properly. At this point, we were able to confirm vertical integration from the Ethernet shield to the motors. After the basic directional tests, we were able to perform various other tests on the robot. We were able to check the chassis alignment and directional consistency using long hallways. Narrow spaces, such as doorways, allowed us to test the maneuverability and response of the steering. Because the robot is meant for non-ideal environments, we took it outdoors to introduce it to different terrains. There, we were able to observe the tire traction and turning abilities, as well as the component's resistance to the jostling created by driving on more rugged surfaces. Being outdoors also gave us the opportunity to test the range of our robot. To test the Arduino code in a more isolated environment, we unit tested the Arduino shields by creating small C and C++ test projects. To test the Silverlight interface, we created a web service that mocked the communication to the Arduino. This decreased debugging time and allowed for concurrent development of the Arduino and the ground control station code. To analyze the costs of our project, we broke the costs into 4 main groups. The core products include the Arduino microcontroller, supporting shields and motor controllers. The core products totaled to $225. To build the chassis, we needed to purchase motors, tires, and other miscellaneous hardware. The total cost of the chassis amounted to $120. The firefighting equipment included the fire extinguisher itself, as well as the electronic motor and other hardware used to engage the fire extinguisher, totaling $53. And our last section includes support materials, such as the router and network cameras, totaling to $157. The total cost of our robot amounted to $555. Initially, our plan was to modify the router to communicate with the Arduino using a serial converter. But we encountered issues compiling programs on the OpenWRT operating system that we had installed on the router, and we were unable to establish serial communication with the Arduino. Instead of continuing with the serial converter, we opted to use an Ethernet shield for the Arduino. This solution created a simple interface between the router and the Arduino, and allowed us to establish wireless communication to the robot. Thanks for watching our project intro video, and we hope that you can attend eWeek this April.
Whee!
Can't wait to see you there.